Kia ora koutou, no mai, haere mai. Welcome to lesson 33 for introductory physics. This is the third of the waves section. We're going to look at some wave phenomena in this lesson. We met waves already, we've defined them, we've looked at their properties. Now what we're going to do is see what some of the phenomena are that result when we have multiple waves or waves in special circumstances, special conditions. Again, this will help us when we get to lights and looking at light waves and phenomena as they relate to light waves. The same phenomena will be present, but that said, there's still some interesting phenomena that we can study just with these waves in general in terms of sound and water and other types of waves. We don't have to just wait for light to really get some interesting things going on. Learning outcomes then, to first of all start talking about how we can describe some of the wave motion using rays and wavefronts. Then to understand the four phenomena that we're going to look at: reflection, refraction, diffraction, and interference. Then we're going to look at a couple of results of those phenomena, including things like beats and standing waves. And we're going to finish with another phenomena called the Doppler effect, and that will also explain bow waves and shock waves, also known as sonic boom. So we'll look at those at the end as well. Firstly, though, as I said, we want to understand how we can describe and illustrate waves a little bit more. We've already met a whole bunch of the properties of waves, so we know what amplitude is, what wavelength, wave speed, and all of that kind of stuff is. But how do we sketch these on a diagram? We can't always be sitting there drawing our little sine curves. That's just not practicable, especially when we have a lot of waves or really short wavelengths and things like that. So what we do is we draw one of two things. The first one is wave rays. And a ray is just like a vector. We're used to vectors, so a ray is just like a vector for the wave. Remember that the wave is the transportation of energy through space or along a medium somehow. Might be a medium, might not. It won't be when we get to light. The ray is just the path that wave is taking. That's all it is. So for a sound wave, like the one pictured here, this is the same GIF we used when we were talking about the sound creation. We were pretending that that grey line was a speaker. The wave here, the energy, is just going straight to the right. So we might just draw a bunch of rays in. Obviously, that wave is taking up that whole space, right? That's some kind of cylinder or container with the black lines being walls. The wave is occurring throughout that whole space between those two walls, but we don't draw one giant arrow that takes up the whole thing, or it wouldn't give us any information. Instead, we just draw a few rays representative of that wave motion. The same way that for an electric field or a magnetic field, we would draw some rays as field lines. Right? We'd draw our force vectors as field lines, but we wouldn't draw them literally. If we would draw a bunch of them so we get the idea of what is going on. Same thing here. We're not going to draw infinite number of these rays along this pathway. We're just going to draw a few to show you what the wave is doing. And so in this case, I've drawn 3, and that lets you know that the wave is traveling from the left to the right, and that it's pretty much pretty uniform everywhere, because I've drawn the rays pretty evenly spaced and all parallel. So the waves are pretty much uniform everywhere. The other thing that we can draw instead of a ray is a wave front. So now what I want you to do is imagine a line. I've tried to draw one onto this GIF, but I did it in a bit of a hurry, and so it's a bit shaky. But imagine a line that just travels along with the crest or compression of the wave. That is all a wave front is. So wave fronts don't make any sense when we're talking about waves on a rope, right? When we flick the string up and down and the wave travels along it. A wave front doesn't make any sense because you just have a single crest traveling along the wave. But in something like the air, the sound wave that we've got below, or a water wave, waves that have 2 or 3 dimensions, then a wavefront does make sense, because you don't just have a single crest traveling along, you have a whole series of crests all lined up next to each other as the whole wave moves along. And so you draw all those crests as a single line, and then you can see how that line would move through space. And that's what a wavefront is. But obviously we can't draw animated diagrams like this when we're trying to describe something. So what we do is we press pause on our system. We imagine we've taken a snapshot of it. We've done that with several things through this course, where we've got something that's in motion, but we sort of pause it just to get an idea of what it looks like and describe that system a bit, with the understanding that in reality it's obviously moving. So we do that here. We press pause and we draw on some rays awesome wavefronts. You normally just do one or the other. I've done both here for illustrative purposes, but normally one or the other is sufficient, but you are perfectly welcome to draw both if you like. The rays and the wavefronts, as you can hopefully imagine, will always be perpendicular. The rays are the direction the wave is traveling, and the wavefront is that line of crests. So all the crests, if you line them all up, because there's a whole bunch of waves all traveling, it's one wide wave, I should say, all traveling along, so that crest is wide, but that crest will always be traveling in the direction of the ray, so that means the line along the crest must be perpendicular to the ray. I've added some little dots onto this diagram. You can see the sine curve there is, if it was, for example, a water wave, it would look something like that. And so we'd draw the wavefronts where each of those successive crests are. And if it was something like a sound wave, then we would draw the crests wherever those compressions are, sorry, the wavefronts wherever those compressions are, which are equivalent to the crests. So that's all the wavefronts and wave rays are. When we are doing diagrams, we sketch them like this, rather than having to draw those little dots or draw all those sine curves. We just draw some rays or some wavefronts, right? You don't draw those dots like I did. Those are just for illustrative purposes. You just draw either the wavefronts or the rays, or potentially both if you really want to. And remember, wavefronts always perpendicular to rays. So we've talked about the idea of sound waves, about water waves. We've talked about waves on a string. But what about the directionality in general for a wave? How does that work? In a string, obviously it travels directly along the string. That's essentially one-dimensional motion. Yes, the string is going up and down, so we do actually have this two-dimensional motion overall, but the energy of the wave is just traveling along the string, just one-dimensional motion of that energy, essentially. Right? The vertical motion is very constrained, right? And if you zoom out enough, it just looks like that little energy is just traveling along the string. So it's essentially one-dimensional motion. Water waves are two-dimensional because they're going across the surface of the water, right? They go across the surface, they might spread out, they might be really wide and travel along a whole big surface, but they are just two-dimensional. There's no way for that water wave to go up into space. But we can get three-dimensional as well, because if we talk about a sound wave, that travels through the air, and that sound wave travels in 3 dimensions. Right? If someone sits on top of a flagpole, as in this example, and claps, right? They sit on top of an example of a flagpole and they clap for our example, then that sound wave is going to spread out. But which direction is it going to spread out? Hopefully you agree it would spread out in every direction. Right? It's going to go every way. There's not just one direction for that sound wave, it goes everywhere. And that is going to be spherical. It's going to be basically a spherical wavefront. Spherical wavefront, it spreads out and travels away from that person. So that energy, the energy that that creates the sound wave, the energy when they clap, they're putting some energy into the air that's transported as a sound wave, and that is spherically transmitted out through space away from them. That type of spherical symmetrical wave is called isotropic. So an isotropic wave just means spherically symmetrical, the same in every direction in 3 dimensionals away from a point. As with many things we've seen in this course, the real world is a bit more complicated, and we don't actually get perfect isotropic waves in the real world. But in some cases, we get things that are very close, and so we can assume they are isotropic because it makes our job easier. It makes the maths easier and the physics easier, and it doesn't really change the result in plenty of cases. There are plenty of cases where it doesn't change the result enough, like this person sitting on a flagpole. The sound wave can't actually travel in every direction equally because there's a person in the way of some of it. If they clap out in front of them, that sound wave, some of it's going to hit them, and so it won't be traveling cleanly on the other side of them. And there's also a flagpole all the way down to the ground, so even if they did it overhead, then straight down is not going to be a very clear sound wave, but it might travel in every other direction equally. So it'd be very close to isotropic. So even though in reality that isn't isotropic, we could use the model of it being isotropic, because if you were to go and sit a kilometer away or some distance away where you can still hear the clap, then that would effectively be isotropic for the purposes of your observation, because you're not directly underneath the flagpole, and that's the only bit that's not isotropic. You could treat it as isotropic. The other thing that's important to know, because it will come up in some scenarios, is the idea of circular waves, but from a big distance. So either circular or spherical, so our isotropic type waves. If you are a long way away from the source, it started out as circular, but by the time you receive it, it will seem to be just parallel straight line wavefronts. I've given an example here. I've drawn a source, a point source. So a point source just means dot, basically, that's creating the wave somehow. And this point source creates circular waves. So it could be three-dimensional, it could be spherical isotropic ones, or it could just be circular waves as I've drawn. The circular waves, as they travel out from that point, will obviously get bigger. The radius will get bigger. And if you're looking just at one section of that circle, then the further away from the point source you get, the straighter that section will appear to be, as you can see if you look at this slide. To start with, they're very clearly circular. By the time you look at the ones on the right-hand side, they are getting very close to being straight lines. They're not quite straight yet because I've only drawn a few on this slide, but you can imagine that if you were that distance again further away, that would be even closer to being a straight line. Another distance that much again, they'd be pretty much straight lines, and you wouldn't really be able to tell the difference between these waves that started out as circular ones and ones that actually just started out as parallel straight lines anyway, because that curvature would be so small, it would be negligible, it wouldn't be noticeable. So that's just an interesting little note on circular waves. If you're looking at them from a distance, they appear to be a straight line. Right? And so sometimes things that appear to be flat aren't. Now we're going to look at the actual wave phenomena. So far, we've just really talked about how waves behave when they're traveling. We haven't really talked about other things impacting the wave and its motion. So what about if a wave encounters an object in its path or another wave that's trying to travel in the same medium? What happens in those cases? We get different phenomena depending on exactly what's going on, and that's what we're going to look at. The four phenomena we'll look at are reflection, refraction, diffraction, and interference. As I said, we will, at the intro slide, we will also then look at some results of these phenomena, some effects that you can see in the real world. And we will also look at the Doppler effect, which is slightly different from these phenomena, and we'll bring that up at the end as well. So the first one, reflection. We're all familiar with reflection. It's the same in everyday life as it is in physics. The idea of something bouncing off something else, it reflects off it. And that is exactly the same for a wave, but in real life, we often just talk about light waves, visible light waves, I should say, when we look at a mirror or something. In physics, any wave can be reflected off a different surface. So reflection is when a wave is traveling in one medium, but hits a different medium and bounces off that other medium so that it stays in its own one it was originally traveling in. And that can happen in strings, not just sound waves or light waves. It can happen in strings as well. The idea of the wave pulse that we met in the previous lesson, if you send a wave pulse down a string, but the end of the string is tied, right? It's tied to a wall or fixed or held in place somehow, that wave pulse will travel down the string, but when it hits that fixed end, it can't keep going. That energy still has to go somewhere because the wave is the transport of energy. So the energy actually bounces off and the energy starts traveling back the other way. So the wave pulse will be reflected. It will travel back down the string the way it came. When you do have a fixed point like that, there's an interesting result, that is the wave pulse is inverted. So if you send a positive wave pulse down, so one that's on this side, then when it bounces off, it will come back and it will be negative as it travels away, right? So it'll be underneath the wave, the string. You don't really need to worry about why that happens exactly, just it's an interesting fact that it does, that it gets inverted. If you do want to think about why it happens, then think about the idea that the fixed end, that grey dot in this diagram, is essentially pulling the string down from where it wanted to be according to the wave pulse. In order to make that string, make that wave pulse all hit that fixed point, it essentially is pulling it down from where it wanted to be according to that original wave pulse that was sent down. So it's pulling it downwards to make it meet that fixed end, which means the new wave pulse going back the other way is going to be below it because it was pulled down, right? So that's sort of why it happens. But as I said, the important point is that it does get inverted. Sound wave reflects in exactly the same way. if a sound wave is traveling through some material, most commonly air, but it can be anything as we saw, and then it hits a different material, it can be reflected. So if you're standing in a room and you say something or you make a noise, then the sound wave will travel through the room, it will hit the wall, and it will reflect off the wall and back to you. And you can hear that as an echo. So when you have a nice room that's very reflective for sound, then you'll get echoes in it. If you're standing at the entrance to a cave and clap, then that sound will travel all the way down the cave. It will reflect off the back wall at the end of the cave and then travel all the way back to you. And so you'll hear that echo, right? And the distance that it takes, it will tell you how long that cave is, because you know how quickly the sound travels through the air in the cave. I believe that's one of the assignment questions, or possibly worksheet, I'm not sure. I think assignment though. When we have multiple reflections, we call this reverberation. So if you have a room that's very reflective and you make a noise and it travels over, bounces off that wall, but then it travels over and bounces off that wall and then back and bounces off that one, and it just keeps doing that off all the different surfaces in the room, and you get lots of these echoes all going on at once, that's called reverberation. And we'll come back to that in the next part of this lecture. If a wave hits a surface and isn't reflected, the energy has to go somewhere. Not all surfaces reflect sound very well. Not all of them reflect light. Not all of them reflect different waves. The energy still has to go somewhere though. Remember, the wave is just the transport of energy. That's all it is. They're just, all the particles are passing along that energy to the next ones. And so that energy is being passed along. It has to go somewhere. It can't get to the wall and then just disappear, because we know energy is always conserved. Energy can't be created or destroyed. So that means that the energy has to go somewhere. Where does it go? Well, it obviously goes into the material. If the wave has stopped, then that material that was in the way of the wave that it hit must have absorbed that energy. In reality, most surfaces will always absorb some and reflect some. It's just the proportions that change. A very reflective surface might only absorb a few percent and reflect the rest. A very absorbent surface might absorb most of it, but it would still reflect a few percent. You're not usually going to get anything that is close to perfect. They can get very, very close. Poor choice of words to say not close to perfect. You don't get anything that's perfect. You get things that are close. Just like we saw with efficiency for machines as well. If the absorbed energy continues to travel in the different material as a wave, so the sound wave hits a surface and none of it gets reflected, all of it gets absorbed. If that energy that gets absorbed is still transmitted like a wave, then we say that it's transmitted, right? The wave has been transmitted from one medium into another. If the energy from the wave that comes in and hits the surface just sort of dissipates and spreads out, maybe heats it up a little bit or does whatever it does, and it just sort of generally spreads out and doesn't become a wave on the other side in the other material, then that's just absorbed. So there's just a slight difference. Technically, the absorption is either still includes the transmitted wave. Right, so absorbed just means the energy is now in that other material. If it's in that other material and still traveling as a wave, then it's transmitted. The next phenomenon we're going to look at is refraction. Refraction is just talking about the bending of waves due to differences in wave speed. Again, this can't work on a one-dimensional wave because the path of the wave is already dictated. It just has to follow that rope, has to follow that string. So it can't happen on those, but it can happen in two-dimensional or three-dimensional waves. What is refraction? Remember that sound travels faster in warm air than colder air. Refraction isn't specific to warm air and cold air. This is just a good example to introduce refraction. What happens if sound wave is traveling in air that has a temperature gradient? So it's got warmer air at the top and colder air at the bottom. What happens to that sound wave? Well, we know that it's going to be traveling at different speeds. So the top, which is faster because it's warmer, is going to travel along a bit quicker than the wave at the bottom, which is colder and therefore a bit slower. That means that the wave fronts will no longer be parallel. They'll start to curve, they'll start to bend away. So that energy is still being carried along, but now it's going to veer off course because one side of it is traveling a bit quicker than the other. Right? So this idea of one side being a bit longer than the other resulting in curvature is something we've met before when we talked about thermal physics. We talked about the bimetallic strips. And if you heat it, one side gets a bit longer than the other and the metal strip curves. The same sort of geometry, same idea here, that one side being warmer travels a bit faster, but now we're talking about a sound wave. So it's quite interesting to see these sort of parallels And hopefully if you understood that, you'll perfectly understand this, even though we're now talking about something completely different. So the wavefronts will start to point downwards, the rays will curve downwards, and we get this bending downwards of the sound wave. If the opposite were true and it was cooler at the top and warmer at the bottom, we'd get the exact opposite effect. We'd get a bending upwards of the wave. And that's all refraction is. It's just this bending due to these differences in wave speeds. And it happens in lots of things, not just sound waves. It happens anywhere where you've got a wave traveling and for some reason there's going to be a difference in wave speed. Before I go on to the next one, I just want to jump to the document camera and just explain one more example. This is not officially part of the course, but it is just another example of wave refraction and an interesting one. If you have water, the water waves travel faster in deeper water. So if this is your water and you're sending some waves down this water, this deeper water, the waves will travel faster, right? So that is going to be faster wave speed over here than it is over here. So the shallower water will be slower waves than the deeper water. And so if you look top down on a pool like this, so you look top down on a pool, and if this is the shallow side and this is the deep side, and you send some waves down, so you've hopefully all seen wave machines or a wave pool where you basically just oscillate this bit back and forwards and it creates these nice waves that travel along in the water, right? Travels along. If you have a shallow side and a deep side in your pool, rather than just being the same depth, then what you'll get is that the shallow side will travel slower, the deeper side will travel faster, and these waves will curve around as well. And you'll end up with these waves that actually curve as they travel along the water. So you can certainly get the exact same phenomenon occurring in other medium. It's not just restricted to air. The next phenomenon is diffraction. So diffraction is also a type of bending of waves, but it refers to spreading out of a wave after it travels through an opening or around an obstacle. So it can't occur again on a rope or a string because the path is already determined, and you can't have an obstacle in the way of a string. It would cut the string in half if you did that, right? So it doesn't work on one-dimensional waves like that, but it works on 2- or 3-dimensional waves. The classic example is water waves going through a little slit. So if you've got a wall in the ocean and the waves are coming in and there's a little gap in the wall, then the waves will travel through and they'll spread out on the other side. And that's exactly what happens. You can go and look at it in the real world. There are videos online. Feel free to go and find them. I've got a GIF here because it's just a bit clearer. We've got these parallel wavefronts coming in on the left of that yellow wall. They hit the yellow wall, which only lets a tiny bit through. In reality, there'd be some reflection of the rest of the waves around in the other parts of the yellow wall. We haven't included that in the GIF just because that would make it very messy to look at, but the reflection would still be occurring there. Whereas the little gap, there's no reflection because there's nothing in the way, so the wave can travel through. But when it does that, it doesn't just stay as this tiny little bit of wave and travel through. It spreads out. That energy spreads out as it goes through. In this case, it will spread out a lot. It'll spread out most of the way, become a nice big arc of curved waves. So that little slit is acting like a new point source of waves. So you get these circular waves coming out from this point source. Again, it can occur in 2 or 3 dimensions, so water waves going through a little hole in a wall like that, or it could be sound waves going through a doorway. That's how we can hear sound from a different room. The sound wave gets to the doorway and it travels through, but because it's traveling through this gap, it then spreads out, and that's why you can hear sound around a corner. If it didn't do that, if diffraction did not occur, then you would never be able to hear someone from a different room unless there was a clear line of sight between you and them. It just wouldn't be able to happen. The sound wave has to bend around the corner in order to get to you. The other thing that does happen is the transmission of sound. If the walls are thin enough, then the sound can get absorbed by the wall, transmitted, and then transmitted from the wall back into the ear on the other side. So you can get transmission. But if you've got thick walls that are soundproofed, you can still hear from around a corner because the sound waves will diffract. They will bend around those corners. This is the same for diffraction around an object. So it might, rather than being a little opening in a wall, it might just be a small block in the way, a small object in the way. And the exact same thing happens. Obviously, you'd get some reflection off the object itself, but the part that goes past the object will diffract and bend around and sort of end up curving past and spreading out a bit after the object. So that happens as well. The amount of diffraction, the amount of bending, there are ways to determine that mathematically. We're not going to do that. I just want you to be aware of the relative amount of spreading out, and that is that the smaller the opening is, the bigger the spreading out. So a small little opening will spread out and become quite circular and quite spread out. As you can see there, it covers a good, I don't actually know what that is, 40 degrees, something like that. It'll spread out quite a lot though, they look quite circular. A larger opening will let more of the wave through, but as a result, it will spread out less. You still get some spreading out, some curvature, but it will spread out less. And whether you call it small or large is how big the opening is relative to the wavelength, right? So it's relative to the wavelength. That means that if the opening is just the same size as the wavelength, then it will spread out a lot. If the opening is lots of times bigger, maybe 5 or 10 times bigger, then it would barely spread out at all and it would just travel straight through. So you need to know the wavelength to be able to predict how much diffraction you're going to get, how much bending you're going to get. The next phenomenon is interference. Interference is when you have multiple waves trying to travel through the same material at the same time. Remember that the waves is the transport of energy. So what we're saying is you might have one person sending some energy down a rope and then another person at the other end shaking their bit and sending energy down the rope as well. Now you've got energy trying to go this way and energy trying to go that way. What happens when they coincide? What does that energy do? That's one example of interference. Of course, it can happen with any kind of wave in any kind of material. If two people are talking at once, you're going to get interference of those sound waves. They're going to be competing for how the air particles will vibrate in relation to those two lots of energy being sent out. So that's interference. Interference is easy to examine with wave pulses. Again, this is why we introduced wave pulses. It makes some of these phenomena easy to see. The example here is a very simple one. We've got one pulse going that way, one pulse going that way. What do they do when they collide? Well, each one is trying to lift up the particles of the rope a little bit, so together they'll lift it up twice as much. It's that simple. That's all they do. We call that the superposition. Superposition because it's the addition of the two different positions, right? Or it could be more. If you had three waves going down the wave and all coinciding, that could happen. So the superposition is just when you have multiple waves at the same spot. You just add them up and see what happens. That's all you have to do. With a wave pulse, it's very easy because we can manually do that. We can look at it and see what that addition is going to look like. Again, there are questions relating to that. So hopefully that makes sense there. If the waves are both positive, like in that little example we just saw, then the amplitude of the resulting superposition will be greater than either wave pulse was on its own. That's called constructive interference. Constructive because it's making it bigger, constructing a bigger wave. Destructive, they destroy each other. That happens when you have two wave pulses or waves that are opposite to each other. So if one of those wave pulses was positive, but the other was negative, negative wave pulse, positive wave pulse, when they coincide, this one's trying to pull the rope up, this one's trying to pull it down, they're going to cancel out and you're going to get no movement of the wave. So you're going to get destructive interference. Of course, it works with full waves, not just pulses. For a full wave, though, it's more complicated mathematically because you have to do that addition everywhere along the wave. You can't just now look at the little pulse and add them together. You've now got to go through and add it together everywhere. But again, it's the exact same process. It's just more mathematically demanding. You just go along and you add them all up. So you can see on this diagram here, to start with, the red one, the red curve is almost 1, the blue curve is almost -1, so they cancel out and we're at 0. The blue one, though, gets positive more quickly than the red one gets negative. So after, I can't tell, the scale's a bit awkward on that, maybe after 0.2 of a second, we have blue being 0, but red is still positive just over a half. So if you add those together, you're going to be just over a half. And then a little bit later, they're both positive and you get the maximum of just over probably 0.65 or something for our resulting superposition. And you just keep doing that all the way along the wave. Usually the waves will be repetitive like this one. And so you do it for one sort of wavelength and then you can repeat that pattern. Sometimes, though, they're not that simple. The one in the worksheet, I believe, is a bit more complex. You'll have to choose a bunch of points for that one. But that's the whole process. You just go along and you say, well, this wave is trying to move it up this much, this one's trying to move it up or down this much, add them together, there's the result. So that black line is the resulting waveform, the superposition of those two waves. It happens with longitudinal and transverse waves. Remember that you could draw the longitudinal waves as a density graph or a pressure graph, right? Either of those look just like our sine waves. If you have the two different density graphs, then that's the sound waves trying to change the density of the air particles. And again, that same process is going to work. They're going to be cancelled out or destructively, or they're going to interfere constructively and get even bigger. So we get the exact same results. So this set of diagrams are straight out of the textbook, but we've got two identical transverse waves. Then they will, if the two crests line up, then it's going to amplify, it's going to be constructive. That's the top row, that third row, C. If the crests and the troughs line up with each other, so they're opposite, then we're going to get destructive interference and they're going to cancel out and we'll be left with nothing anywhere if those two waves are identical but not quite lined up. So the crest and the trough were lined up instead. The exact same things happen in rows B and D with longitudinal waves or sound waves in this case. In B, we've got two sound waves with the compressions lining up and they become even bigger compressions. They become more dense for those compressions and we get an increased intensity, increased amplitude. Remember, that's what amplitude was. Amplitude was more compression and more spreading out for that rarefaction. And row D, we get the opposite. If one wave is trying to make the air particles a bit denser here and a bit more spread out here, and the other one's trying to make them more dense here and more spread out here, you're going to cancel out and end up with the same density everywhere, which is like having no wave. So we get longitudinal and transverse waves both exhibiting all those interference properties. The name we give to those waves when you have crests lining up is in phase. So the crests line up and we get that constructive interference. When the crests and the troughs line up, so the crest of one wave and the trough of the other, and then the trough of the first wave and the crest of the other, when they all line up, that's called out of phase, and you get the destructive interference. That last comment there is just a little point that if you have two waves that have the same wavelength and the same wave speed, then their relative phase can't change. If these two waves are both traveling this way, they've both got the same wavelength, then this crest and this crest will both be in line for both of them. If they're both traveling with the same wave speed, then this crest might move here over some time. The other one will also move here. So they'll just forever be in phase. So if they started in phase, they can't get out of phase. If they started out of phase, they can't get in phase. So if they've got the same wavelength, the same wave speed, then they can't change phases. Of course, you can get in between. You can get partially in phase or partially out of phase. Like that example a couple of slides back, this one here, they are not in phase or out of phase. They are, yeah, the peak for the red one occurs slightly after the peak for the blue one. I was just trying to figure out which way it went. You can see that the trough for the blue wave is just left of the zero, and the peak for the red one is just to the right of our zero axis. So therefore, they're not quite out of phase. They're close, but they're not quite out of phase. What happens then if we have two identical waves, but they're traveling in opposite directions? So we said if they're traveling in the same direction with the same wavelength, same wave speed, they'll always be whatever phase they are, they'll just stay that. What if they're traveling in opposite directions? What happens then? We have to repeat that interference process, but now we have to do it for a series of snapshots. So take a snapshot of the two waves, do the interference pattern, let them move for a tiny bit, take another snapshot, do the interference again, move a tiny bit, take another snapshot, and so on and so forth. Again, mathematically demanding, we don't expect you to do that. That's stuff we would use computers for, but the result is very interesting. What happens is that we get this resulting pattern, and it's known as a standing wave. It's known as a standing wave because you'll see that there are some points that are always zero, and in between those points, we get this wave that goes big positive and then big negative and then big positive again. It just oscillates up and down. And it looks almost like SHM at each of those points. And it is, in fact, SHM at each of those points. But that is called a standing wave. It doesn't look like it's moving left or right, but it's the result of two waves, one moving left and one moving right at the same time, with all the properties being the same except opposite directions. And that's a standing wave. And again, they are very fascinating and they're fundamental for music. So as I said, we will look at some results of those phenomena. We've met the phenomena, and now we're going to talk about some of the things that we can see in the real world. The first one is just a comment that there is a whole field of study about acoustics. It's a huge field of study. People spend their entire careers working on acoustics, and especially people designing performance venues. They need to be very careful about placing materials in the right places to try and direct the sound waves, to cause them to reflect out into the audience and provide a good sound experience for someone in the theatre, but not to be constantly echoing everywhere, and also not to be absorbing it all. So it's a big challenge to try and get the sound effects correct. Not sound effects as in movies, but sound effects as in the effect on the wave of the room that it's in order to fully appreciate those sounds being created. Noise cancelling headphones, these are quite common and they're becoming more popular as time goes on and technology gets better. Noise cancelling headphones take a little microphone from the outside of the headphone that can hear, the microphone receives sound waves coming towards the headphone from other sources. So you might be outside and there might be someone playing a stereo over the road and you don't want to hear that. The microphone in your headphone will pick up that sound and it will play an inverted wave. So the exact opposite. So that it plays a crest whenever there was a trough and it plays a trough whenever there is a crest, and it cancels out that wave because that's what interference does. And that's all noise cancelling headphones are actually doing. The better they are at it, the more precisely they can match those crests and troughs up and cancel out that noise exactly. What about if we've got two waves that are very similar but not quite the same? We said if they were exactly the same, then they'll always be in phase or they'll always be out of phase. But what if they're not quite the same? What if one of them has a slightly different frequency? We're going to assume they have the same amplitude for now, but what if they've got slightly different frequency but the same wave speed? So let's take a snapshot again. So we're pushing pause. We'll forget the wave speed for a moment. Push pause. Have a look at this scenario. Right, we've got two waves, very similar frequencies, but not quite the same. To start with, we're going to line them up so that we have a blue peak and a red peak. And we're going to see what happens as we continue. You can see already that very quickly they will start to get out of phase, but they're not hugely different. So by the time they've done one wavelength each, they're just a little bit out of phase. By the time they've done two, they're more out of phase. By the time they do three, they're even more out of phase. And depending on how close they were, will determine how many wavelengths it would take to get fully out of phase. You can see here that after 1, 2, 3, 4, 5 red wavelengths, we've only gone 4.5 blue wavelengths. So we're now perfectly out of phase after 5 red wavelengths, which is only 4.5 blue wavelengths. So that's a reasonable difference in wavelengths. You can imagine the same thing would occur if you had waves that were closer. It might take 50 red wavelengths and you might only do 49.5 blue ones in that time. So it would take more wavelengths, but the same thing would still eventually happen. So if the two waves are very similar but not the same, then eventually, if they start in phase, they will end up out of phase as you travel along the wave through space. But remember, we've pushed pause on this, so we're not talking about the wave speed yet. This is about the wavelength difference. If we do our superposition of that, what we'll see is that they start out being constructive when they're in phase, but by the time we get to them being out of phase, we've obviously got destructive and we've got zero amplitude. And it decreases as you go along, and you get this green wave resulting. Starts out being positive, big, and then it doesn't get quite as far down or quite as far back up, and it gets smaller and smaller. It sort of decays a little bit, it gets smaller until it ends up at zero when we get to that destructive interference. And if you do that over and over, this graph is a little bit hard to read. I didn't do the contrast very well, but you can hopefully pick out that the green wave starts big, gets small, but then of course the waves are still going to be these different wavelengths, so they'll end up back in phase again, and so it gets big again. So the green wave, the superposition, gets big again, and then it gets small again, and then big again, and we get this oscillation of the amplitude. Right? The frequency of that green wave turns out to be the average of the red and the blue one, right? The average of those two. That's not specifically important, but it's the green wave has a consistent frequency, a consistent wavelength. It just is the average of the other two. What's important here is the amplitude. The amplitude starts out big when they're in phase, drops to nothing when they're out of phase, gets big again, and then small again, and then big again, and so on. And it repeats that pattern. And this pattern is called beats. All right, not beats as in music, as in keeping beat, but beats as in the varying amplitude of the wave. And so the amplitude gets bigger and then small. Now remember that when we press play again, these two waves have a wave speed, but they've got the same wave speed, so they travel along together, which means that beat pattern, that superposition pattern, is just going to move along at that same wave speed as well. So that wave traveling through, those two waves traveling through that medium, will actually produce a wave that looks like this, like these beats. And so these beats sound, for sound, the amplitude is the thing that we hear, it's the loudness. So if they are sound waves, then what we hear is one frequency, one pitch. We interpret it as a single pitch, a constant pitch, but we hear the loudness pulsing. The loudness changes because the amplitude is the loudness. So it's loud, then it drops to nothing, and then loud again, and then nothing, and then loud again. So we get this varying loudness, this pulsing loudness. And it's very useful for tuning musical instruments, because if the two frequencies are close, then there'll be beats. As they get closer, as you tune the instrument and get them closer, the beats slow down even more, because it now takes more wavelengths for them to get out of phase. So that means the beat takes longer to drop to nothing and then back to maximum. And when you finally get them perfectly in tune, the beats disappear because they now can just stay in phase the whole time. So that's what beats are. And I'm actually going to show you beats on a website. I will put the link to this website on stream, so you can have a play with it yourself if you want, but hopefully it'll come through clearly on this video. What I've got here is just an online tone generator. I'm not going to attempt to pronounce the guy's name, but he's made this free online tone generator, and you can just play any specific tone. So it's just a perfect sine wave of a sound wave. By opening it in two different tabs, what I'm going to do is I'm going to play two different sound waves. I've got 440 hertz here. Remember, that's 440 oscillations a second, and this is 444 hertz. So 444 oscillations a second. So they're very similar, but they're slightly different. Because the speed of sound is the same, because these are both being played into the same ear, it doesn't matter exactly what it is, it's going to be the same speed of sound. And we know that V equals F lambda. These slight changes in frequency are going to mean we get a slight change in wavelength, and we're going to hear beats. So I'll play the 440 hertz first, which it's quite an annoying sound, just a pure tone, but that's the 440 hertz, and I will add on 444. So what you can hear is those beats, the loudness pulsing in and out. So that loudness is pulsing. The note itself that you're hearing is 442 hertz. It's between the 440 and the 444. But you're hearing, the point was those beats, that pulsing loudness. And the other thing I said was that as you move closer to the other one, the beats slow down. So let's try that. I'll play 440. This one's 444. We hear the pulsing, and then we will move down. And you hear the beats slow down. And then when we end up at the same tone, the beats stop altogether and we just have one constant tone. So that is very useful, as I said, for tuning musical instruments, but also just for gauging whether two frequencies are the same. How quick those beats are will tell you how spread out the frequencies are, how different they are. Right, we're most of the way through this lesson now. So that was the application of beats. Then we've got standing waves again. So remember, standing waves were two identical waves traveling opposite directions along a medium. When we want to create a standing wave, we need some way for the wave to travel back and forth along the same medium. But remember that reflection, if you have a string that's fixed at one end and a wave travels along it, it reflects, and it becomes an identical wave traveling back the other way. It's inverted, but if it's a wave rather than a wave pulse, that doesn't really matter, because an inverted wave still has crests and troughs, just like the incoming wave had crests and troughs, right? So an inverted wave will still look exactly the same as the incoming regular wave before it was inverted. So what that means is that if we have a piece of string that's fixed on both ends, and we send some energy down it, that wave will reflect at this end, and then go back and then reflect at that end, and it will sit there and go back and forth. So one wave being reflected back and forth over and over can actually end up looking like both, because it's traveling in both directions, it gives you the same effect as if you just had two infinite waves both traveling in opposite directions. So you can set that up perfectly. If you get the right frequency to wavelength ratio and the length of the string right and all of this, if you set it up perfectly, then you can create standing waves on a piece of string. And that's what musical instruments are. When you have a piano, it's hitting a string that's the right length to cause a standing wave of whatever frequency you want, and so on. Looking at that GIF a bit more, we'll see that there are some spots. I'll go back to those 2 slides in a moment just to go over them again, but we'll see that there's some spots where there's no movement. No movement, we call it a node. The other spots in between, we get this movement of the string going first up and then down and then back up and then back down and so on and so forth. The positions where it reaches maximum displacement, we call the antinodes. So nodes are no movement, antinodes are the maximum movement. So going back just to show you the text that I've got there, we've got the spots with no movement called nodes and the spots with maximum amplitude being called antinodes. Same thing can occur in sound. So this GIF is very much like the one we saw of creating sound in a tube, but now we've got a closed end on it. And if you do that, then you can create a standing wave in the sound in the air as per that animated GIF there. So it's exactly the same idea. It's harder to see in the animated dots that we've got at the top there. But again, if you plot it as being a pressure graph or a density graph over time, then it will look just like the standing waves we saw before. So as I said, if you use a piece of string and you send a wave down it that's the right length so that it interferes with itself correctly to become a standing wave, then you can create harmonics. And that is that you might have the wavelength being the right size to make this pattern that you're seeing here, a single antinode between 2 nodes. The 2 ends have to be nodes because they're fixed. The 2 ends of the string are tied. That's how we're getting that reflection. So they have to be nodes. They can't move. And so the simplest thing you can do is have a single antinode. And that means the simplest wavelength is twice the length of the string. This wave here, the one you're seeing, has a wavelength of twice the length of that string because we're looking at just a half of a wavelength. Right? That's half of a wavelength. If you then want to go and give it a bit more energy, make the wave travel a bit faster, then you can introduce extra nodes. And so you can actually see this if you've ever played with a bit of string or an elastic band or something. If you shake it, you can get those sort of harmonic, the fundamental harmonic going, the single up and down in the middle with the ends being sort of stationary. Obviously, you have to move one slightly to cause the wave. But if you do it a bit faster, you can actually cause two little antinodes, and you get an extra stationary point in the middle. I don't have a little demonstration set up for that at the moment, but I'll see if I can add one as a video later on, maybe find one on YouTube. And of course, you can keep going, make it a bit faster wave, and then get a third harmonic and a fourth harmonic, and so on. And so the number of harmonics is just basically saying how many antinodes you've got. Fundamental harmonic, 1 antinode. Second, you've got 2 antinodes. Third, you've got 3, and so on. And you just keep adding a node and an antinode each time. The wavelength then is pretty easy to calculate. If it's n harmonic, so your nth harmonic, then the wavelength is 2L over n. Feel free to have a play with this formula, look at the diagram on the previous slide and satisfy yourself that it's correct, but it is. So if you know the length of the string and which harmonic you're putting into it, you can just use this formula to find the wavelength needed. As I promised, the last section is on the idea of movement between waves and sources or observers, and it's relating to the Doppler effect. The Doppler effect is an increase or decrease in the observed frequency of any wave when the source and observer move towards or away from each other. And I've kept it separate from the other phenomena because those just refer to waves in general. This is specifically talking about the creation or the observation of waves. If you've got a source producing waves, the observer will see the waves exactly as the source is producing them. There's nothing surprising there. But if one of them is moving, then the observer will see the waves as being a different frequency than they are emitted. This, on the left, we've got the source being stationary, producing some number of waves every second. Suppose it was 1 every second. Let's say it had a frequency of 1 Hertz. Produces a wave, another second later, it produces another one, and it would look just like this. Remember, that's a snapshot. The observer here, when they hear that first wave, suppose they take a step forward, that means that they'll hear that second wave a bit sooner than if they had stayed at the same position, because it would take a whole second for the wave to move to the observer. but they've moved forward to meet it. So it's going to take less than a second to hear that second wavefront. And then they take another step. It'll be less than a second to hear that third wavefront and so on. So the frequency is now greater. They hear them at a higher frequency. The same thing would happen if the source was moving towards the observer. If they release one every second, but they're moving towards the observer, then the observer will hear them more regularly, more frequently than one every second. They'll hear more than one every second. And that's all the Doppler effect is. But if you think about something like a boat on water creating waves, the thing producing the waves could end up traveling at the same speed as the waves themselves travel. So if you create a wave, but then you travel at that same speed, the wave never gets away from you. You keep going with the wave, and then you create another one, right? But you're still where that first wave was. So now the first and the second wave are overlapping. They're on the same place. You get this constructive interference. You move along with it again, create a third wave front, third crest. That's another one added on. You're getting this extra constructive interference, and you build up that constructive interference, and it builds a sort of a wall right in front of them as they travel along with the waves. If they travel faster than the waves, then they've now gone beyond that wave front, right, when they create the next one, and you get this kind of scenario happening where you get this sort of this bow wave, this wall of waves forming up behind them instead of right at them, right? So if they're traveling at the same speed as the wave, they'll get the wall right in front of them. If they travel faster than the wave, then it'll sort of spread out as a V behind them. And this is very common to see with boats traveling through lakes and bodies of water. They will travel faster than the water waves do, and so the waves spread out behind them and make this sort of triangular pattern. The faster the boat or the source is traveling, because it's not just boats on water, it's any sound, any wave, including sound. The faster that source is traveling compared to the speed of the waves in the medium, then the narrower the V will be, because the further away from that wave it'll be when it creates the next one. And so the V will get narrower as per the diagram on the right. A shock wave is exactly the same idea, but for an object creating sound and traveling faster than the speed of sound. That's all a shock wave is. And so you've heard of sonic booms. That's what a sonic boom is. A sonic boom is the observation by us as observers of this shock wave. So remember that a sound wave is a variation in the pressure, right? The particles bunch up, get a high pressure. The sound wave at the front of a plane is doing that, right? It's building up this really high pressure bit, and by the back of the plane, it's a low pressure bit, and then it returns to normal again after the plane. So you get normal pressure up to the plane, high pressure at the front of the plane, low pressure at the back of the plane, and then normal pressure again afterwards. And that means that if you are standing in the way of this shock wave, that you get a sudden change in pressure that your ears interpret as this really loud boom, because it's just a really sudden change in pressure, which is what sound is. So you get the sudden change in pressure, you get a really loud boom, and it sounds like the sonic boom, which is what it is. The thing to note, though, is that a sonic boom is not just a sound that's made as the plane breaks the barrier, breaks the sound barrier. It's not just the plane gets through the sound barrier, makes a big boom, and that spreads out and people hear it. The sonic boom is our experience of that cone, that shockwave cone traveling past us. So that that shockwave, that cone travels with the plane the whole time. It's flying faster than the speed of sound, and you just happen to hear it as this boom. So the little diagram here, again, straight out of the textbook, I believe, for this one. But person C has already heard the sonic boom because the shockwave has passed them. Person B is hearing it now, and person A hasn't heard it yet, and they'll hear it as the plane travels past them. So that's the end of this lesson. We've covered quite a lot of material here, including how to physically draw diagrams of waves, and then a whole bunch of different phenomena and some of the results of those phenomena. So there is a lot of information in this lesson. The key, though, obviously, is to understand the different terms and the different phenomena and get a brief understanding. I don't expect much detail, but a brief understanding of those different phenomena and how they relate to those reflection, refraction, diffraction, and interference. So think about standing waves and what we've got in terms of reflection and interference both occurring, things like that. So try and tie all of that stuff together in your mind.